Hello and welcome back to Anton Math. Now we just finished talking about multiplication and division of complex numbers in their polar form. Now we're going to extend multiplication a little bit and see how we can deal with different powers of complex numbers. So let's go ahead and take a look at what happens when we try to figure out what a power of a complex number in polar form is. So first let's look at z times z, or z squared. And this, of course, is where I'm saying my z is going to be equal to, in polar form, r times cosine theta plus I sine theta. So we'll keep using this same z throughout this exercise here. So z squared is z times z. We know from my definition of multiplication, this means I have r times r cosine of theta plus theta plus I sine of theta plus theta. Simplifying this down, we see that our z squared is equal to r squared cosine of 2 theta plus I sine of 2 theta. Okay, so now we have a formula for z squared. Now what if we want to find z cubed? Z cubed, this is z times z squared. So using our result from above, we see this is going to be r times r squared cosine of theta plus 2 theta. I'm using my result. We know what z squared is, so I'm taking the modulus of z squared is r squared. The argument of z squared is 2 theta. And I have plus I sine of theta plus 2 theta. And so we get that z cubed is equal to r cubed cosine of 3 theta plus I sine of 3 theta. Now if we were to continue this and keep increasing this number in terms of integers, we go 3, then 4, then 5, we see this pattern emerging, and we eventually see that z to the n, for any integer n, is going to be equal to r to the n, should say for any positive integer n, times cosine of n theta plus I sine of n theta. And this is our formula now for taking an arbitrary power of a complex number, and this result here, this is called DeMoivre's theorem. And this is what we call DeMoivre's theorem. And let's see how we would do this in practice. Now, this isn't always the most useful thing to do. If I have, very simple z and I'm just taking it squared, it may not necessarily be the best thing to convert it to polar form and then apply this theorem and then convert back out of polar form to figure out what my number is. But for large powers, this is extremely useful. Let's take a look at an example here. Let's say I want to find 1 plus I to the 20th. Now I could write 1 plus I next to itself, multiplied by itself, and have 20 different 1 plus i's listed out, but that's going to be an extremely long way to solve this problem, isn't it? To use DeMoivre's theorem, notice all I need to know about 1 plus I is I need to know its modulus, and I need to know its argument theta. So let's go ahead and jump in. Let's call this 1 plus I to the 20, let's call this z to the 20. So my r for this z, this is equal to the modulus of z, which here is going to be the square root of 1 squared plus 1 squared. Remember, not I squared, because I is not my b. My b is the coefficient of I, which in this case is 1. So we're going to have that r is the square root of 2. And I have that tangent of theta is equal to b over a, which in this case is just 1 over 1. So my tangent theta is 1. Now a is greater than 0, and b is greater than 0. So that means I'm in quadrant 1. So that gives me a theta. I'm looking for a theta where tangent of theta is 1. and theta is in quadrant 1, and we know that theta is pi over 4. So now I'm ready to solve this. 1 plus I to the 20, this is equal to, in its polar form, the modulus, which we found to be square root of 2 to the 20, times the sum cosine. Now here for cosine, remember we are multiplying theta by n, whatever n is. Here our n is 20, so this is 20 times pi over 4. And then we have plus I sine of 20 times pi over 4. Now we can simplify a little bit. Let me do this modulus simplification over to the side. The square root of 2 to the 20, if I go ahead and square root of 2, I'm going to factor out a 2 from this 20, use my exponential laws. This is the same thing as 2 to the power 10. And all you computer science majors out there should know that 2 to the power 10 is 1024. This is the number of megabytes in a gigabyte, right? Or kilobytes in a megabyte. We should be very familiar with this number if we're doing anything computer science. Now this 20 times pi over 4, the 4's cancel and I get 5 pi. So 1 plus I squared. We found this to be 1024 on the outside for my new modulus. I have cosine of 5 pi plus I sine of 5 pi. That's it. This is the polar form of 1 plus I to the 20th. I keep writing squared here. We're doing something much bigger than squared, aren't we? This is to the 20th. Now, usually if you're given a question in form a plus bi, which is what we were given, our z here is 1 plus I, which is not in polar form, we want to give an answer that's also in the form a plus bi. And remember, the way we go from polar form to a plus bi is we have this modulus on the outside, and we evaluate the trig functions on the inside of the polar form. Now cosine of 5 pi, that's coterminal with cosine of pi, so this is going to be negative 1 plus I times sine of 5 pi, and sine of 5 pi is 0. So our final answer in a plus bi form is just negative 1024. We can rewrite it here. 1 plus I to the power 20 is negative 1024. Now, I suggest that you go and try to do this problem without using polar form. It will really give you a very nice appreciation for this tool we've developed to finding these very large powers of complex numbers. We can do this very quickly and without too much work. All we have to really do is find the modulus and find theta, and then take the modulus to n, multiply theta by n, and we have our solution. Now I'll do some more examples of this in the example video at the end of the section, but that's it for now, and in the next video we're going to talk about nth roots of complex numbers. So we're going to take this DeMoivre's theorem and we're going to apply it now to rational numbers 1 over n for some positive integer n. So we'll see you there.